first part of Objective 2 takes those graphs that are familiar to us, the linear, the absolute linear, the quadratic, and the exponential growth. But now it's going to move the graph either left or right, or up or down. So let's start with just the characteristics of this first graph. Just by looking at the equation, we know that it's a linear equation. X is to the first power, y is to the first power. And so in the parent graph, y equals x, the key point is 0, 0. But there have been some things that have been changed to the equation. When you look at this new equation, there's this -1 right behind the x, and it's trapped in the parentheses. It's doing something. It's shifting that key point 1 unit to the right. And then this +2 that's at the end of the equation, it's shifting the point up 2. So therefore, instead of the key point being 0, 0 on this graph, the key point is actually +1, +2. So we're going to graph it, +1, up 2, and there it is right there. And now, what's the 3 doing? Well, it's the leading coefficient out there, so it's just the slope. So from that point, we're going to go up 3, 1, 2, 3, over 1. And then we'll make our line out of it. And there we go. We're looking at something like that. But again, the key point isn't at 0, 0 anymore. The key point is at +1, +2 because of the translation. It's the opposite of what you're looking at here and the same as what's happening right there. And that's going to be a consistent idea throughout the entire course. Now moving on to the next example, example B. Again, from the characteristics of the equation, we know that this is an absolute value linear, so it's going to make a V. But it isn't this V, because a couple of things are changing. The slope is not 1, it's -1/5. And then again, what is this x -3? What's this -3 doing directly with that x? Well, it's shifting the key point 3 units to the right, but there is no up or down shift because there's no either plus or minus back here at the end of the equation. So if you think, here's where the key point should be in the parent graph. But if I shift 3 units to the right, 1, 2, 3, my key point is now going to be, here's 0, 0, 1, 2, 3, and there's no up or down shift. So my key point is simply going to be 3, 0. So what's the -1/5 doing? Well, it's the slope again, but since it's negative, this V isn't going to be going up. It's going to be going down. So down 1 over 5 looks something like that. Down 1 over 5 should look something like that. And if I had, a true XY axis with grids and everything, it'd be looking a little nicer, but this is what has developed out of that. Right there. Now, the next equation in example C. Just by the characteristics of the equation, we know it's a quadratic. It's going to make a parabola. Y equals x squared would be the parent function, and it would look something like this. The key point would be 0, 0. However, it's been shifted. So what has been the shift? Well, x plus 4 is going to make it go left 4, because remember, it's always opposite of this, same as that. So left 4, and then 3 down. So if you think the key point, which would start off at 0, 0, goes 1, 2, 3, 4, 1, 2, 3 down. There's the new key point. That's the vertex. The vertex is at -4 and -3. Now we know it's an up parabola because the 2 is positive, but if you want to get an idea of what are 2 other points that are going to make the parabola work a little better, well, that's where you can break out the XY table if you want. Instead of using x equals -4, what if we went one more to the left? X equals -5. Well, plug in -5. -5 plus 4 is -1. -1 squared is +1. 1 times 2 is 2. 2 minus 3 is -1. But what if we went 1 to the right of -4, -3? That would make an x value of -3. So if we plug that in, -3 plus 4 is +1. 1 squared is still +1. 1 times 2 is 2. 2 minus 3 is -1. So the 2 next points, lattice points, would be -5, -1, -1, -2, -3, -4, -5, -1, and -3, -1. And it's an up parabola. Also, it's going to look something like that. Now, again, the last one's going to be the one that's a little bit trickier, the exponential growth graph. Because for one thing, the key point is not at 0, 0 in the parent graph like all the other ones. The key point is at 0, +1. But we have to explain that, what's the translation? What's happening in the graph to move this key point? Well, x plus 1 right up here would be an indication of 1 unit to the left, because remember, this is always opposite, but then the -4 is going to drop it down by 4. So there's the translation of the key point, 1 to the left and down 4. Now, when it comes to exponential graphs, there's one other thing that's going to drop 4 also, and that's this asymptote. The asymptote right now is at y equals 0. Well, it's going to drop 4, like that. So this red line is going to end up down here. See, -1, -2, -3, -4. So there's your new asymptote. Now, there's a lot of things you can do if you wanted to say that, if you wanted to look at it like this, if I translate this graph 1 to the left and then down 4, I would be at -1, -3. And just to verify that, you could make an XY table. What if you plugged in -1 right here? Well, -1 for x. -1 plus 1 is 0. 3 raised to the 0 power is 1, because anything raised to the 0 power is 1. And 1 minus 4 is -3. So -1, -3 is where that key point moved to. Now, if you want to know maybe just one more point, well, why don't you plug in x equals 0? When you plug in x equals 0, 0 plus 1 is 1. 3 to the first power is 3, and then 3 minus 4 is negative 1. So we'd be at 0, negative 1. We'd be at about right here. And even if you want to go a third point, plug in x equals 1. 1 plus 1 is 2. X equals 1. 1 plus 1 is 2. 3 squared is 9. 9 minus 4 is 5. So 1, 5 would be another point. 1, 1, 2, 3, 4, 5, somewhere about up right here. Now remember, this is the asymptote. The asymptote is at, it dropped 4. So the asymptote is really now y equals negative 4. That's this line right here, this dotted line. And that just means the graph is going to do this. Remember, it's an exponential growth graph, so to the right it keeps growing. And when it comes down here on the left, it gets closer and closer and closer to that asymptote, but it never touches it. So there you go. I believe this will get you through the first 9 problems, the first section of worksheet 2. The next part of objective 2 deals with what we call composite functions. And all that really means is plugging one function into another function. So on E, example E right here, I have f of x defined as x squared plus 1, and I have g of x defined as x plus 4. So find and graph, this notation is saying f of g of x. The way you read this, you read from the inside out. So what this is saying is take the entire g of x function, which is the x plus 4, and plug it into the f function. Now, if you're plugging something into a function, the only place that something can enter a function is at when I say a window opens. Well, the window opens at the variable, in this case, the variable x. So when this window opens, the x plus 4 can enter the function right there. So what that makes is the new equation. You could say y equals if you want. Y equals. Now when the x plus 4 gets plugged in right there, it now gets squared because that's what the function says to do. So x plus 4 quantity squared. And then we've got this plus 1 at the end of it. Now, the characteristics of this graph are that it's a parabola. It's a quadratic equation. And the vertex, the key point on this graph, is going to be at negative 4, positive 1. So, negative 1, negative 2, negative 3, negative 4, positive 1. There's your vertex right there. Now, if you want to figure a couple of other points, you can make an XY graph. But here's where something you can remember. If the leading coefficient is just a 1, all that means is the next lattice points are over 1, up 1, both directions. Over 1, because this is an up parabola, because it's a positive 1. If it were a negative 1, it'd be a down parabola, and you'd go over 1, down 1. And here's our parabola, or a good representation of it. Here's our parabola right there. Now, let's review domain and range. Parabolas open, forever and ever to the left and forever and ever to the right, or at least this parabola does. So the domain would be negative infinity to positive infinity. Now the range, on the other hand, this parabola has a minimum value. Its lowest point is at y equals positive 1. So we write the range with a closed bracket because we actually do hit positive 1. So the low point is positive 1 and the high point is infinity. Move on to example F. Example F has two more functions that are named j of x and k of x. And this is asking you to find j of k of x. So again, it's just saying work from the inside out. Take the entire k of x function and plug it in where it can. That's where it enters the j of x function right there. So what we end up with is an equation that says this: y equals 4/7 x minus 5. And there's nothing, after this. So this is an absolute value graph. It's going to make a V. The key point is at positive 5, 0. So the vertex is at positive 5, 0. So 1, 2, 3, 4, 5. There we go. Now the 4/7 is the slope. So we can go up 4. 1, 2, 3, 4, 5, 6, 7. There's that point. And we can do the exact same. We can go up 4 and go over 1, 2, 3, 4, 5, 6, 7. And that'll make roughly that point right there. And connect them, make the graph. And there we go. Now domain and range, again, open forever to the left, open forever to the right. So the domain is negative infinity to positive infinity. The range, this time the lowest point on the graph is at y equals 0. But it goes up forever and ever. So it's positive infinity on the other end. Here are a couple of examples that could be helpful for problems 16, 17, and 18 on Objective 2, describing translations. Now, I started off with, again, what most students consider to be the hardest graph, the exponential growth graph. And remember what that exponential growth graph does as far as the parent function is concerned. The key point is not 0, 0. The key point is right here at 0, 1. Now I've marked it, but we're actually not going to use it. Let's look at the f of x function first. You can tell by looking at the function, that the equation, that the shift is 3 units to the left because of this x plus 3 right here. So we're going to take where the key point normally is at 0, 1, and we're going to shift it 3 units to the left. So there's my new key point. Now, there is no up or down shift because there's nothing else in the equation. So if I were to just sketch that graph, and the asymptote, can't forget the asymptote, is right here at y equals 0. If I were to sketch the graph without plotting in any other points on the graph, it would look like that. Now, let's go to the g of x function. If you look at the g of x function, it doesn't have a left or a right shift because all it is 2 raised to the x. So that puts us back at a starting point of 0, 1. We don't go to the left, we don't go to the right, but the equation is telling us to go down 5 units. So if I go down 5 units from what would be the key point, 1, 2, 3, 4, 5, I'm right here at 0, 4. Now remember something else that shifts. The asymptote drops 5 also. So instead of the asymptote being right here at y equals 0 on the x-axis, the asymptote has now dropped 5 units, and it's now at y equals negative 5. So here's the key point. Here's the asymptote. So the graph looks something like that. So there are the two graphs, f of x and g of x. Now the big question is, what's the translation to get from f of x to g of x? If you've got good enough graph paper, you can just count it out. You can also do a little analysis of those key points. The key point on the f of x function in red, remember, was negative 3, positive 1. The key point on the g of x function, the one I did in green, was 0, negative 4. So then you can ask yourself, well, what does it take to get from negative 3 as far as the x-axis is concerned? What does it take to get from negative 3 to 0 on the x-axis? Well, it takes 3 units to the right. And what does it take to get from positive 1 to negative 4 on the y-axis? If you were at positive 1 and you ended up at negative 4, what did you do to get there? You dropped 5. And that would be your transformation right there, from f of x to g of x. From f of x to g of x. That's what you do. You go to the right 3, you go down 5. Now the last example I've given you from the characteristics of the equation, it's an absolute value equation and the slope is negative. So you already have an idea of what both of these are going to do. And since they have the exact same slope, really what we're going to do is we're going to make the same graph twice, only in different positions. By the fact that they have the same slope, you can kind of call them the same graph, except in 2 different places. Now, the f of x. The vertex of the f of x downward v would be negative 4, negative 1. So f of x has a vertex of negative 4, negative 1. So we might as well plot it. Negative 1, negative 2, negative 3, negative 4, down 1. And the slope is down 5 over 3. So we could go 1, 2, 3, 4, 5 over 3. Put us about right there. And so our f of x graph, down 5 over 3. There's our f of x graph. Now, the g of x graph. It's going to look really similar to this, only in a different spot. The vertex of the g of x graph is going to be positive 2, negative 4. So 1, 2, 1, 2, 3, 4. It's going to be somewhere around right here. And it's going to have the exact same slope. down 5, 1, 2, 3, 4, 5 over 3, and then down 5 over 3. So here's our g of x graph. Wait for the lights to adjust. And now all we have to do is figure out the transformation. What does it take to get from the f of x graph to the g of x graph? Now let's look at it just from the vertices. If my x is at -4, and then it moved and became +2, what had to happen to get it there? Well, to go from -4 to +2, you've got to go 6 units to the right. And then if my y-coordinate was at -1, but then it ended up at -4, what had to happen? Well, I had to drop 3 more. So 6 units to the right, 3 down, and there's the transformation right there. Hopefully that's enough. If you're having a little trouble with the last 3 problems, 16, 17, and 18, hopefully that helped.